There will be some small deviations.
Discrepancy. That's where the information is.
That's where the information lies. Those small discrepancies will then point the way towards newer particles, which we have missed out in this count, and newer types of thinking will arise. Newer choices will be. We've tabulated the choices possible. I was showing this graph yesterday of the possible choices, 1, 2, 3, 4. Which choice nature will take at the moment, we do not know. We can only make guesses and so on. Then after this is done, then there is the other side of the joining together. This is still electroweak.
Yes.
Then there is the other side of joining of the strong nuclear force and the gravitational force with the electroweak.
That's right.
The strong nuclear force is a very terrible thing to join together. The only experimental work is the proton decay,
yes,
which you are carrying experiments in Bangalore at the Kolar.
Yes.
Unfortunately, these experiments are getting nowhere. They are terribly difficult to perform because of the background of neutrinos. A neutrino can go right through the Earth, yes, without being at all reflected.
These are experiments which are underground to filter out the cosmic rays, but neutrinos still get in. Neutrinos still get in, and they make interactions.
And this is impossible to obviate them. So either you go to the moon and do the experiments there, where the neutrino flux is 1/100th of what it is on Earth, or you just make the detectors very large and hope for the best.
Or make them much more intelligent. Supposing you could measure the energy very accurately, that it is a proton mass and no more or no less.
Could be. But anyhow, these experiments are not getting anywhere, so that's one of our sorrows. Then there is the possibility of final unification, that's of gravity, together with these forces, these three forces.
Of course, you haven't explained to our listeners how is proton decay connected with unification.
Well, that's, you see, if the proton is the same particle as the lepton,
yes,
the lepton being the electron.
That's right.
You see, previously, in the electroweak theory, the protons and the electrons are treated separately. If they are the same particle, then one can transform into the other.
Yeah.
And we can tell what the age of this transformation should be. It should be greater than 10 to the 30 years.
Yes.
Since the life of the universe is only 10 to the 10 years,
yes,
that of course doesn't affect the fact that we exist and so on. However, it's a very important concept for which we would not like to lose, because this explains many things. Why, for example, we don't have antiproton stars and
that's right,
things like that.
Here, really, the kind of physics one is interested in is being given to impact the whole of cosmology, or vice versa.
That's right.
One could even do cosmological studies.
Well, yesterday I was saying to my audience in Bangalore that physics used to be a troika: theory, experiment, and accelerators. Now it's a quintica. Why? Because astronomy, astrophysics, has joined particle physics in making one single subject. We can, all the early universe from 10 to the minus 43 seconds up to 10 to the minus 12 seconds is comprehended by particle
physics.
The fifth element in this, the new element, is the mathematics. It's amazing. We did not have to care. See, Ray Yost in the 50s used to say, all the mathematics a physicist needs is a rudimentary knowledge of Greek and Latin alphabet so that he can put indices onto his equation. That's no longer true. We really now need the most modern mathematics.
Yes.
Algebraic topology, Riemann surfaces, things of that variety. Very modern mathematics.
Yes.
Top grade mathematics. And that is a very new thing. It's happened in the last 5 years. This whole development has taken place in the last... So, going back to my unification stages, the last one is the gravitational unification, and that is the most difficult. We did not have any real good ideas till last year, till 84, till the end of 84.
What happened in 84?
And in the end of 84, two men, one an Englishman Green and one American Schwartz, they discovered that there is two theories only, which they call the string quantum theories, the string theories, in which you do not talk of single particles, but whole strings which are created and annihilated. And those strings, these strings are nothing very mysterious. They are, suppose I have a quark here and an antiquark here, then the force between them is, we think of it as something which is momentarily passing across.
Yes.
But these people assert, no, it's like a string tying the two together. And then you start worrying about the oscillations of that string. And the amazing thing is that those oscillations, the lowest oscillation is gravity. It's incredible. It's incredible.
The string has all possible forces in it?
No. Let's tie a string between a quark and an antiquark.
Yeah. Actually,
it's slightly more complicated. You have to, don't think of a quark and an antiquark, think of it as a round string, just by itself. And endow each point with a fraction of a charge. Charge density. Right. Now take the string. Assume that it's a solid object. Let it oscillate. It will have all manner of oscillations. Take the lowest possible oscillation, zero frequency.
Except you have to give certain properties to the string.
Tension is the only property which you need to give it. Only one parameter. Tension. That tension, in the limit that tension becomes infinite, or the inverse of the tension goes to zero, you discover that this string represents the force of gravity. It's a difficult concept to get into. And we don't know the reason. That's the funny thing of it. Nobody knows the reason why this is happening, why gravity of all forces.
But where do the mediating particles, the Higgs bosons and all kinds of things come in to make it so?
Well, I'm coming to that in a minute. So, now this string has to live. It cannot live in less than 10 dimensions. That's another funny thing. If you wrote its equations of motion in 4 dimensions, they'll be inconsistent. So it's 10-dimensional gravity we are talking about. 10-dimensional gravity is the same thing, if you like, as 4-dimensional gravity plus strong, weak, electroweak forces and so on. So this is the connection which we make. And then all the quarks and stuff comes out once you do this. It's the most exotic theory. Now, we have hopes from this theory that this will prove to be finite. That hope, if it's not fulfilled, we shall all leave it. So in another year, you may find nobody wants to talk about it. Or in another year you may find that this is the final candidate, or say at the moment the final candidate for the theory of everything. So this is the sort of stage you reach. Now you'll ask, how will you test this theory? What distinguishes this theory, apart from predicting the stuff which we know already, 45 particles plus 13 messengers of force and so on? What else does it do? Unfortunately, we do not know quite well how to get this theory down to 4 dimensions and get other predictions. One prediction which was made in the beginning of January, this last year, 85, was that this will predict another Z0. One more Z0. Now that prediction has become a bit doubtful. It's still there, but it's not unique. There may not be a Z0. So at the moment, if you ask me what is the new characteristics which you will measure from this theory, I cannot tell you.
I see. But it is not, you said that it should be finite, but it doesn't predict things, but if new things are found, it could incorporate other things which are found.
At the moment it is incorporating everything which we know about physics.
And no more. We don't know.
We don't know. You see, as I said, there was the prediction of one thing more.
Yes.
But that's no longer compelling. Somebody has found another solution of the equations of motion in which those predictions are not compelling anymore. So we really have still to learn how to deal with... This is a type of mathematics which certainly was invented by Riemann. Then Teichmüller is a German Nazi soldier who did lots of work on it during the war.